Hello, my name is Yong Kwon and this is my 7th project for CAP 6110. For this project, I chose the paper Foveated Instance Segmentation, which has been accepted to the conference CVPR 2025. The paper presents a novel approach to instance segmentation for augmented reality and virtual reality devices, by leveraging the real-time user gaze, applying segmentation only on the region of the user's instance of interests. This design choice not only reduces the computational overhead of segmentation, but also enhances its performance. For augmented and virtual reality, segmenting and recognizing objects in their user's view is crucial for seamless interaction between virtual and real content. For example, an augmented reality headset might need to identify a chair or a table in front of the user to overlay graphics correctly. Despite this importance, the segmentation task poses substantial computational challenges, mostly due to the limited resources of devices, and the high resolution of input images.
The authors measure this cost of segmentation on Jetson or in NX, a widely used edge GPU in augmented and virtual reality environments.
As shown in the figure, applying segmentation to an image of size 640 can result in latencies over 300 milliseconds, and some architectures such as Segformer even goes over a second. This is far beyond the 50 to 100 milliseconds latency budget needed to maintain a smooth experience. Reducing the image size to 64 helps the latency, but degrades the accuracy performance. To solve this problem, the authors observed that augmented reality users don't care about every pixels at the same time, and have a relatively narrow focus region. For instance, a user might be looking at a coffee mug on a table, but would not pay attention to the chair at the corner, until he turns his head to explicitly look at the chair. Specifically, during augmented reality experience, a user will exhibit a pattern of fixations and saccades as the user moves their head or eyes. A fixation is when the user's eyes are focused on a single point, while a saccade is a rapid eye movement to the next point of interest, which tends to last about 20 to 200 milliseconds. The authors decided to exploit this tendency. Specifically, by prioritizing segmentation only to instances of interest, it is possible to reduce processing workload and computational costs. And since most augmented and virtual reality devices support eye trackers that can update gaze data with small latency, using it to improve segmentation can greatly improve the user experience. The authors further validate their claim through a detailed study on the ARIA dataset, which consists of users' field of view and gaze movement data. After grouping similar frames as segments, the authors show that 95% of segment frames have a gaze difference below 0.1, displaying potential of using gaze data to reduce computation. The authors present FovealSeg, a foveated instance segmentation framework that uses the user's gaze direction to guide an efficient segmentation process. Specifically, segmentation is applied solely at the instance of interest based on the gaze, and the segmented results are reused across frames with similar frames with same gaze locations. Because this aligns with foveated rendering, which enhances graphical performance by rendering only the regions of interest with full resolution, the name FovealSeg was used. To do so, the authors had to design a pipeline with a deep neural network that focuses on the gaze location, while reducing any redundant computations. The authors first present FSNet, a plugin-type neural network that can be attached to any existing segmentation backbone such as Segformer to use gaze information during segmentation. Given a high-resolution image from the device camera and the user's gaze point within the image, the network outputs a segmentation mask only for the object at that gaze location, ignoring everything else. Internally, the model first generates a gaze map, where each pixel's value indicates how close it is to the gaze point. This map is sent to a saliency neural network, which produces a weighting over the image, which is used to downsample the image so that the interest region is kept at a relatively higher detail. The segmentation model is modified to output a binary mask and a classification for that one object, which is way simpler than a full multi-class segmentation. To account for the relative small focus region, for training the loss is weighted by the inverse of the area. Also, the saliency model is trained first, then the segmentation model is fine-tuned. This is the overview of the FSNet architecture during training. To deploy the FSNet over a video stream, the authors designed a pipeline that decides when to run segmentation, and when to skip based on the gaze change and frame difference. Specifically, when a saccade is detected during a session, the segmentation computation is skipped. When the gaze is fixed, but there is a notable pixel difference, the instance segmentation is updated, otherwise the last segmentation is reused. These are the evaluation results of Faville-Seg against other methods. While Faville-Seg was motivated to be an efficient framework, it also shows significantly better results than baseline approaches. In terms of computational efficiency, Faville-Seg reports up to a 75 times reduction, and takes around 84 milliseconds for a seg-former backbone, which previously took around 2 seconds. Overall, these results demonstrate Faville-Seg's efficacy and effectiveness in making augmented and virtual reality a better user experience. In conclusion, we introduce Faville-Seg, an instance segmentation method tailored for augmented reality, by leveraging real-time gaze data from devices, showing notable efficiency improvements along with enhanced performance. Thank you for listening.